So today we're going to talk about a generic performance problem that affects OCP platforms. And I'm going to go into a bit about how we saw this problem manifest in our production environment and how we detected it and figured out what it was. And Zhengyu is going to tell you a bit about what's actually going on in the platform layer and how it can be fixed. So at Facebook, we run a variety of OCP platforms. And this performance issue is very generic because it actually affects all of these platforms. And it probably affects some non-OCP platforms as well, but haven't tested those, so not 100% sure. Basically, this problem manifests in a number of different ways that at first glance aren't obviously all the same issue. But once we sort of understood what was going on, we were able to trace this back to attribute this problem to a lot of things we were seeing in production. So the first issue I recall digging into related to this was we were working on the availability of our cache systems. And caches are very low latency, so you typically have a very short timeout talking to a cache. And we were noticing that we would have these error spikes of timeouts on our cache hosts. And we normally, if there's an error, like a timeout, it's either there's something overloaded or it's some issue in the network. But in digging into these, the systems were not overloaded and there was nothing wrong in the network. So something strange going on these machines. We just didn't know what it was. Another example of a problem that we noticed was our database master promotion process. This is a process where you have one database instance that is a master for some data, so that's the one you write to. And we have to transition that role over to another database instance. This is a very time-sensitive and critical process that has to succeed or it causes lots of errors. And we noticed that the failure rate for these promotions was sort of higher than we expected it to be. And in particular, some machines would fail it much more often than others, which was very strange because they're all running the same software. And another sort of example of the type of problems that this performance issue caused is when we have systems that have to connect to like a remote data center or over a high latency link. We would see spikes in connection failures, largely due to like the packet loss of the SYN packets because it takes a long time to retransmit those, and that a lot of time causes just connections to fail. And again, this would be specific to certain machines and not really looking like an actual network issue. So we didn't know what was really causing it when we saw all these symptoms at first. But the theme here with all of these is that these issues sort of degrade the reliability of the systems over time. And kind of the key point here is that a degraded system, a degraded machine is much worse than a dead machine. You know, when a machine dies cleanly, our systems are designed to sort of fail around it. But when a machine is just degraded and occasionally unresponsive, it's actually much worse because it'll stay in production and cause a low rate of errors over time, especially if you have a lot of machines in this kind of situation. So one day we found a machine that was particularly affected by this problem. It was very slow, and so we were digging into doing a deep dive to try and understand what was really going on with it. And one of our engineers had a great idea to look at kernel scheduling latencies. So kernel scheduling latency is basically the time it takes for a process to actually run once it's ready to be run. And it's typically very fast, like less than a millisecond. And maybe on a really busy machine, it gets upwards to like, say, 10 milliseconds, but the order of magnitude for this is pretty small. And when we did this performance analysis on this really slow machine, we found that the scheduling latencies were very strange. Every process on the entire system had a massive delay in scheduling latency at the exact same time, in the order of hundreds of milliseconds. So this is very unusual. And it basically just looked like the machine completely stalled for hundreds of milliseconds. And not only did it do this once, it was doing it repeatedly. So this sort of explained all the symptoms we had been seeing. But we had to dig deeper to understand what was really going on. So we wrote some detection script. You can see in pseudocode on the right here. That is a pretty simple way to detect this problem. It's basically just sleeping in a loop, and the idea is you just check for how often you overslept. So the script sleeps for 100 milliseconds, and if it wakes up 500 milliseconds later, that's a very good sign that there's a problem. So we deployed this script to our fleet, and we were amazed at the number of systems that were affected by these types of stalls. Very large portion. The good news is most systems, it was very infrequent, like a couple stalls a month, not a big deal. But as with many things, there's sort of a 90-10 distribution going on, and 90% of the stalls are happening on 10% of the machines. And those 10% of the machines cause a lot of problems in production, cost a lot of engineering time debugging issues. And one quick note about this detection approach is it's entirely possible to get sort of false positives occasionally for cores that are very busy on a machine and have a scheduling delay. So to make it more robust, if you do this kind of detection on every core on a machine, and you can correlate that all of them stall at the same time, it's a very high signal that you have this problem. So once we had this detection rolled out to our fleet, we started looking at all the examples we had, and we pretty quickly noticed that there was a strong correlation of these stalls to hardware errors. And the thing about the hardware errors is that many of them are correctable, meaning they're sort of functionally transparent. They don't cause any application failures or anything like that. It's just it takes a moment to correct the error, typically very fast. But what we were seeing was a bit different. So like if there's a correctable memory error, it doesn't make sense for that to stall a machine for 800 milliseconds. So something else is going on there. And Zhengyu's going to dive into sort of what's going on at the platform layer.
Thanks, Chris. So errors makes performance suffer. We are no stranger to this topic. Only this time it could be different. There are many properties of a hardware error that cause performance impact. The type of the hardware error, the severity of it, how frequent it is it persistent, and so on. So among all those performance impacting aspects of the hardware error, the handling of the hardware itself is the one can be easily missed. To understand how hardware error handling can cause system performance impact, let's take a closer look on how this error handling is conducted in the system. There are three major tasks a hardware error handling solution needs to perform: detect the error, report the error, and apply mitigations to the error. Those tasks are not isolated to a specific agent within the system. In fact, responsibilities are shared across all system stack, from software and application layer all the way to the hardware layer. And each layer has its own focuses. The software and application layer is mainly responsible for the front end of the error handling, meaning it's focusing on harvesting failure information and apply the mitigations from the software and application perspective. The firmware layer is mainly responsible for the back end of the error handling, meaning it's the main workforce to detect error happening in the system, satisfy the desired policy to expose those errors to the upper stack, and guide how hardware should behave upon those error occurrences. The hardware layer, sitting at the very bottom of the system stack, is mainly responsible for providing the capabilities of how error could be detected within the system, and what actions can be taken from a hardware perspective. All these three layers need to work together to present a full error handling solution. Upon close investigation of the different error handling tasks within different layers, the system management mode and system event log, commonly used by firmware to perform while performing the hardware error handling tasks, drew our attention. For those of you who are not familiar with the system management mode and the system event log, system management mode is an operating mode commonly found on x86 and the x64 processors. It is intended to be used by firmware to perform low-level system management operations. Upon entering this mode, all CPU cores within the system will do context switch, and only one core will be directed to perform the system management tasks. The firmware implemented hardware error handler resides in this space. The system event log is an out-of-band log kept by BMC. Its format is defined by industry standard IPMI spec, and its content is customizable to fulfill different event logging needs. It is usually created by BIOS and sent to BMC through IPMA commands. It should be noted here, the IPMA commands used to send the system event log can be expensive. So the takeaway here for these two features are, system management mode will cause all CPU cores within the system to context switch. And the system event log used IPMA commands can be costly and cause long latency. So with all that being said, let's take a look at how firmware implemented error handler can cause system performance impact. When a hardware error happens in the system, an interrupt called system management interrupt will be generated and cause system to enter in the system management mode, where the firmware implemented hardware error handler will start to execute the error handling tasks. One of the many steps within this error handler is to collect error information and create the error-related system event logs, and then send to BMC using IPMA commands. Depends on the implementation, several system event log can be created, and several IPMA commands will be used. If you recall from the previous slides, the IPMA commands used to send the system event log can be a long latency operation. So in this case, a combined large latency would be observed if several IPMA commands are used to send the several system event logs to log the hardware error. And don't forget, all those latencies are occurred while system is still in the system management mode, where all CPU cores has been context switched and not doing any software or application jobs. So from software and application perspective, system will be stalled. The larger the number of system event logs used to log the hardware errors, and the longer the unit time length each IPMA command will use to send the system event logs, the longer the system will stall. This is a generic behavior and a general problem across OCP platforms due to the fact this issue resides in the error handler implemented at the common firmware layer. To minimize this performance impact, our targets are clear. We need to minimize the number of cells used and created while system is still in the system management mode, and we need to minimize the time needed for each IPMA command to send the system event log. To be able to achieve that, we identified 3 strategies that can be carried out by the firmware. First, we need to switch from the occurrences-based hardware error system event log reporting to failure event-based. Second, we need to consolidate and standardize the information needed to log the failure and make it scalable. Third, we need to apply optimizations to the IPMA communications among different system agents to shorten the communication latency. Here is an example of how we implemented those strategies in the firmware on OCP platforms. For BIOS, an algorithm can be implemented in the hardware error handler to track the count and frequency of the hardware errors. So 2 general failure events can be reported here: the high frequency hardware error burst and the low frequency hardware error tracking. In addition, a unified format can be used to regulate how system event logs are generated in the hardware error handler. So the number of cells used for the hardware error handler can be controlled and desired. For systems equipped with bridge IC, return first mode can also be carried out by the bridge IC firmware, where instead of return the acknowledgement of the serial login request back to host, only after the receiving of BMC's serial login confirmation, the bridge IC firmware can return the login request back to host, returning the acknowledgement of sorry, I got a mouthful. Can return the acknowledgement of the login request back to host as soon as it receives the request from the host, and then pass the request to BMC to finish the logging. This will largely save the wait time needed from the host side. For BMC side, optimization is also identified, where the BMC firmware can be improved to return the acknowledgement faster. The enhancement can be made to return the acknowledgement earlier in the cell logging flow, where once the data has been acquired for the IPMI daemon. This would also save the latencies of the host waiting for the completion of BMC writing the data into the cell. With all those three strategies in place, we tested this new firmware error handling solution in our OCP platforms, in 3 different OCP platforms. The system store measurements are measured against 3 different hardware errors: the PCIe non-fatal uncorrectable error, PCIe correctable error, and memory correctable error. The results show the performance impact of system store due to hardware error handling can reduce significantly. The average system store time per failure event can reduce from hundreds of milliseconds to as low as 2.3 milliseconds. This is a big performance improvement. For the completeness of this firmware solution, we would also like to share the verification methodologies we adopt to allow the assessing and ensuring of this solution's effectiveness on the OCP platforms. We recommend to use a hardware error injection to test out this solution and strategy. And the performance measurement can be acquired using the system store measuring method we mentioned earlier. And also, we also recommend that the errors should be injected in a randomized fashion, where it can exercise all possible scenarios. In summary, hardware error handling cause system performance impact is a common problem across OCP platforms. The improvements can be made as a common firmware layer, and it is applicable to different OCP platforms. And most importantly, the development and validation of the firmware solution for the hardware error handling needs to be system performance aware. The work to be contributed to OCP will include the IPMI cell hardware error record format and the bridge IC firmware return first model, plus the BMC firmware at quick cell processing flow. We recommend to check the system store in your OCP platforms and identify the correlations between the system store against those hardware error occurrences, and adopt this solution, firmware solution presented here to see improvements. Questions? Yes.
So will you be making any modifications to OpenBMC to?
Hardware-wise, I don't think so. There'll be firmware modification in there.
And so would you contribute that to OpenBMC?
We have submitted the spec to the OpenBMC community, and is waiting for approval. Yeah.
Is it possible to handle some of the errors in the system software instead of via SSMI?
Sorry, say again?
Is it possible to handle some of the errors, for example, in the Linux kernel and not in the via SSMI?
Yes. So there are trade-offs. For handling of these errors using the kernel or the OS native method, the trade-off is the information or the first-hand response cannot be carried out in the Linux kernel, where firmware actually have the first stage of solving or mitigating those errors. That also will prevent the pollution of the error environment data if Linux can come in later. So we recommend to use the firmware first model to handle these errors. Yes.
Can you talk a little bit about bridge IC?
Excuse me?
The bridge IC.
Yes.
Can you talk a little bit about
Which part? You want to, so,
that physical IC which is there between BMC and host?
oh yeah, so bridge IC is a hardware equipment that's sitting between the host and the BMC. And it's widely used in the multi-BMC system, multi-host systems. We can talk offline with more details on that. Yes.
Now everything, most of the Intel servers handle this using SMI, right?
That's correct.
Yeah, but now if we design a dedicated call to handle this error and this code.
That's right. So if the other architectures do have the capability to dedicate some resources, including cores or memories, to be able to handle this hardware errors without interrupting the system service. Yes, there are architecture can do that. For this particular case, the performance impact is caused by the correctable errors and the non-fatal uncorrectable errors reported in the system. So they are more prevalent when the errors happen in the system. So we're focusing on those errors. For other errors like machine check errors and like network errors or something like that, we haven't been able to identify performance impact being correlated to that. So, but that could be investigate further, yes.
So are you just stopping at identifying the error and you are fixing it by correlating with the possible causes, right?
Right.
Is that loop kind of automated or is it kind of still manual?
You mean the detection phase using the system store?
Detection phase is like definitely like automated. You have to run some script on it. But after that, once you find an error, so the fixing part, is that still manual or is it automated?
The fixing part.
I mean the error handling part, handling.
Oh, the handling itself. Yes, the handling requires the firmware change, right? Firmware change will be changed from BIOS for BIOS and the bridge IC and the BMC. And once if a change within firmware layer got implemented, this handling process is automated. Yes.
So that handling part, that the firmware updating, that is also automated.
You mean?
So you identify an error, and after that, the system update and whatever you just mentioned, that part is automated, or somebody has to go there to do that remediation?
Yeah, remediation part. So depends on what kind of remediation mechanism or method you use or you implement in the firmware. But that's all in the firmware and software layer. No human or manual interruption needed in there. Yeah.
This will be part of your OpenBMC Q3.
Yes, yes. We are submitting this to contributing this to OpenBMC first. Yeah. Yes.
So the BIC in the middle, basically that one do all the coding directly BMC and filter out all the error and then so basically my question is there any delay response with the new approach?
No, that's exactly so. One of the problems is like bridge IC is acting as a middleman to receiving requests from the host and passing requests to BMC. This communication process is causing adding up the delays or latencies in the system. The proposed approach here is to cut that latency and decouple this dependencies from the host to BIC and BIC to BMC. So the host to BIC part can be accomplished first, and then BIC to BMC part can be accomplished later.
So acknowledge right away.
That's right. Okay, thank you very much.